Some of this is going to be review. Hopefully, if it's not, we're in trouble. Hopefully, a lot of this beginning part here is review from Chem 101 on the types of intramolecular bonds. Yeah, let's talk about that. So, in Chem 101, in first semester chemistry, we talk about bonds that are inside molecules. And those are technically called intramolecular bonds or forces. Intra meaning inside, okay? Like it's intra, it's inside. Um, the main type of intramolecular forces that hold molecules together are ionic bonds, right? That's what holds metals and nonmetals together. It's an exchanging of electrons. The metal gives electrons to the nonmetal. The metal becomes a cation. The nonmetal becomes an anion. And the ions group together and hold themselves together in this thing called a crystalline lattice. So everything I just said there should like hopefully be reviewed, right? Ionic bonds, some from the left of the periodic table, some from the right of the periodic table above the staircase, bring them together, they exchange electrons, cations, anions, blah, blah, blah. The other force that can be inside a molecule is a covalent or molecular bond. I don't care what term you use. And this is between two nonmetals when they share electrons. So a covalent bond is when two nonmetals share electrons. They can share 2 electrons. That's a single bond. They can share 4 electrons. That's a double bond. They can even share 6 electrons. That's a triple bond. Covalent bonds can get a little more complicated, and this is going to be important. We are going to need this for tonight. A covalent molecule can share the electrons unequally or equally. So just because you're sharing something does not mean you have to share that something 50-50, right? Somebody can hog it and still share, right? So a polar covalent bond is when the two nonmetals unequally share the electrons. Somebody's going to hog the electrons. That's going to result in a dipole moment. We're going to talk about that in a moment. A non-polar covalent bond is when they actually share the electrons 50-50 or darn close to 50-50. We'll talk about what the cutoff is in a second, but that's when they share the electrons like 50-50. Okay, this is like a utopian ideal scenario sharing, but it's almost all, usually that's not the case. That should all be reviewed. How can we predict well, first, let's back up. How can we predict if two nonmetals are going to share electrons equally or unequally? Well, what we can use is a table of electronegativities. So electronegativity is a scale that goes from, well, it really goes up to 4.0. So electronegativity. What electronegativity tells you is how much an atom hogs the electrons, okay? Electronegativity goes up to 4.0. And the atom with the highest electronegativity, the valedictorian of electronegativity, because I like to think of electronegativity as like, GPA. Okay, like the way GPA used to be, not this stupid weighted GPA thing that they do. It doesn't even make any sense. My school, Manheim Township, they don't even give out class rank anymore because it would hurt somebody's feelings. They found out that they weren't, you know, whatever. It's just like, gosh, it's ridiculous. Anyway, I digress. So, fluorine is valedictorian. If you look at a periodic table, fluorine lives right here. Fluorine has got an electronegativity of 4.0. Nobody messes with fluorine. Nobody. When fluorine makes a bond, it's hogging the electrons, unless it's bound to another fluorine. Then they're going to be in a stalemate. Okay, but fluorine, oh, he's a bully. Fluorine is a bully. It hogs those electrons. People always say, well, are you going to give us a table of electronegativity values on the test? And I'll only give you the electronegativity values if the atoms are like right next to each other on the periodic table. If they're not right next to each other on the periodic table, you don't need an electronegativity table. Here's why. Okay, noble gases, they don't have electronegativity values because they don't make bonds. They're noble gases, right? Okay. As you move away from fluorine, the electronegativity drops off quite drastically. So that means as you go in this direction and as you go in this direction, the electronegativity start to drop off. For example, oxygen right next to fluorine, 3.5. Chlorine right below it, 3.0. Nitrogen right over here, 3.0. Carbon, 2.5. It drops off drastically. As you move away from fluorine towards francium, the electronegativities drop off. Okay, so francium has the lowest electronegativity on the periodic table, other than the noble gases that have a full octet and don't want to bond anyway. And then fluorine has the highest electronegativity. The only two atoms that are not identical that I want you to memorize have very similar electronegativities are hydrogen and carbon. Hydrogen does not really belong here. Hydrogen belongs right over here above carbon. And hydrogen has an electronegativity of 2.1. That's going to be really important. So carbon is 2.5, hydrogen is 2.1. We're going to talk about why that's important here as soon as I erase some stuff. Here's our scale for polarity. Difference in electronegativity. If the two atoms have a difference in electronegativity of 0 to 0.5, we consider that bond to be a non-polar bond. If the two atoms have an electronegativity difference that's greater than 0.5, but less than 2.0, we consider that to be a polar bond. And if the two atoms have an electronegativity difference that's greater than 2.0, you're probably ionic, right? You probably like if the two atoms have such vastly different desires for electrons that the difference between them is greater than 2.0, then you're probably an ionic bond. Okay. So why the carbon to hydrogen thing? Here's why. Carbon 2.5, hydrogen 2.1. That's a difference in electronegativity of 0.4. Does carbon want the electrons that it's sharing a little more than hydrogen? Sure it does, but not much. Okay, very, very little. So little, it wants it so, carbon wants the electrons such a minuscule amount more than the hydrogen that we just say they essentially share these electrons 50-50. In the real world, do they really share them like 55-45? Yeah, but we're going to consider this joint custody. Okay, that's not good enough. This is 50-50. Okay, so it's right in here. So the carbon to hydrogen bond is a non-polar bond. It's such a special bond that we have a name for it. It's called the hydrocarbon bond. And I would like you to memorize that. Hydrocarbons are non-polar. That's going to be really important because the strongest intermolecular force that they're going to be able to have is a London dispersion force. That's coming. That's coming. Give me 10 minutes. Okay, but hydrocarbons are non-polar. Other than that, for non-polar, the only other time that I'm going to hold you responsible for non-polar, unless I would give you electronegativity values, would be if the two atoms are identical. So for example, like a molecule of Br2, that's a non-polar molecule. You don't need to know any electronegativities, right? Bromine bound to bromine. I don't care what the electronegativity of bromine is. It's 2.8. Someday you'll memorize electronegativity values too. But anyway, I don't care what the electronegativity values are. These two bromines are going to hog those electrons 50-50. Okay, this bromine wants it as much as that bromine. They're the same type of atom. They are in a stalemate. That's a 50-50 bond. Even fluorine, if I have a molecule at F2, nobody wants electrons like fluorine. But the problem is this fluorine wants them just as bad as that fluorine. If you have two identical atoms bound together covalently, then it has to be a non-polar bond. It has to be. Hopefully this sheet is not brand new for you. And if you made it through Chem 101, it certainly shouldn't be. Now, you might have had a slightly different sheet Okay. This is the one I like. This is the one I learned back in high school ages ago. So these are the shapes for molecules that have a central atom. If the molecule doesn't have a central atom, you need group theory. And that's like, if you're going to go on in chemistry, you get to learn how to talk about the geometry of molecules that don't have central atoms. But there are certain geometries that can be nonpolar. I'm going to use the word can be because they're only nonpolar if the x's, the atoms that are not in the middle, are identical. Okay, so this one, for example, this linear geometry can be nonpolar. Okay, so for example, this would be like carbon dioxide. So if I draw carbon dioxide up here, here's our Lewis structure for carbon dioxide. Two lone pairs on each oxygen. Hard to make lone pairs with this thing, but you get the point. Carbon dioxide is a linear molecule, electron domain 2. The C to O bond, very polar, right? So if I look at one of these C to O bonds, carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. That's a difference in electronegativity of 1.0. That falls in the polar range, right? 0.5 to 2 is polar. So this is a polar bond. Here's the thing. Each of these C to O double bonds is polar. However, the molecule overall is nonpolar. Here's why. This is like vectors in physics, if you ever took vectors in physics, or forces in physics, right? Okay, two opposing forces that are identical cancel each other out and result in no net force. Here's what's happening. This oxygen on the right is pulling on the electrons in this molecule in this direction. But this oxygen on the left, since it's identical, is pulling in this direction. And the end result is that there is no polarity in this molecule. This molecule contains polar bonds, but is non-polar overall. I know, that's crazy. What are the other shapes that can be nonpolar? Well, the trigonal planar molecular geometry can be nonpolar. If all three of those X groups are the same, that would be nonpolar. They'd cancel each other out. The tetrahedral molecular geometry can be nonpolar. That's a very important one because a carbon that has a valency of 4 that's making 4 bonds, if all of those X's are the same, like carbon tetrafluoride, you could imagine if we had a carbon in the middle and then 4 fluorines, each one of these X's is a fluorine. Carbon in the middle. Each one of those carbon to fluorine bonds is incredibly electronegative. Fluorine 4.0, carbon 2.5. It's a difference of 1.5. Very polar bond, but they're going to cancel each other out because they're equally spaced, 109.5 degrees apart. There's going to be no net polarity to this molecule, and it'll be nonpolar overall. It's pretty remarkable. Some other ones, really, we're not going to go above domain 4. And when you take organic chemistry, carbon cannot exceed a valency of 4, but just for your, just for completeness, the trigonal bipyramid can be nonpolar if all X groups are the same. The octahedral can be nonpolar if all X groups are the same. The square planar can be nonpolar if all X groups are the same. And let's see, this linear guy here can be nonpolar if all X groups are the same. So molecular polarity, more complex. Now, the second that you have a lone pair on your central atom, except for the square planar molecular geometry is really special, or this linear one, the second you have one lone pair on your central atom, you're automatically polar. It's not symmetrical anymore. So hopefully molecular polarity, that was some review from Chem 101. Hoping that was some review from Chem 101. So now that we've hopefully reviewed covalent bonding, we've reviewed polar covalent bonding, non-polar covalent bonding, and we even just hopefully reviewed molecular polarity, which is a little more complex. Okay, now we can start to talk about intermolecular forces. So everything we just talked about so far has been an intramolecular force. Let me pull this up here. Where are we at? There we go. Everything we talked about is an intramolecular force. These are forces or bonds that are inside molecules. What I want to talk about now are intermolecular forces. In fact, I absolutely positively hate using the word bond here. So I would like you to not use the word bond. That's a pet peeve of mine. Most books have stopped using bonds, right? When I started making these slides 10 years ago, they were a bit, Now we like to use the word forced. Okay, so for intermolecular, we like to call these forces. And the reason for this is I like to reserve the word bond for things that are inside a molecule, intramolecular. But I like to use the word forces for attractions that are between molecules. Okay, and that's exactly what an intermolecular force is. An intermolecular force, we call them an IMF for short. An intermolecular force is a force of attraction that holds two molecules together in the condensed states of matter. So it's not inside a molecule, it's two different molecules, and it's a force that's gluing the two molecules together. Where do you see intermolecular forces? You see them in the solid and liquid phases. We call the solid and liquid phases of a substance, we call those the condensed states of matter. And the condensed states have intermolecular forces. Think about it, okay? If I have an ice cube, okay, solid water, solid H2O, there must be some force that is gluing these trillions times trillions times trillions times trillions of water molecules together, right? Okay, I mean, in an ice cube, even a speck of ice, there's more molecules of water than you could possibly ever imagine. Okay, remember a mole is 6 times 10 to the 23rd or something, right? So in 18 milliliters of water, you got 6 times 10 to the 23rd molecules of water. It is absurd, right? If I have a piece of ice, there must be something holding all those water molecules together. Same thing goes for liquid water, right? I've got this cup of liquid water here, right, that I brought up before my wife brought me my coffee. Okay. But there's something holding these water molecules together. They're not just flying out of here, they're staying in this cup. Right now, some are evaporating, right? And in fact, when evaporation happens, you break some of the intermolecular forces. You break all the intermolecular forces when that happens. But what's gluing these water molecules together? What is holding them together? Well, the answer is an intermolecular force. The gas phase, however, has no intermolecular forces, and that is incredibly important to understand. Gases have no IMFs. When a substance is in the gas phase, the molecules act independently. They don't interact at all. There's no interaction between particles in the gas phase. The molecules are individual entities. They do not interact. Um, when a phase change occurs, when we melt, okay, or we vaporize, or we sublime, or when we condense, or freeze, or depose, okay, when a phase change occurs, what's happening is you're actually breaking or creating intermolecular forces. Okay, when we go from solid to liquid, we break some intermolecular forces. When we go from liquid to gas, we break all the remaining intermolecular forces. When you go from gas to liquid, you make some intermolecular forces. They now hold the molecules together. And when you go from liquid to solid, you create a whole bunch of intermolecular forces because now it's solids have a definite shape. And that's because there's more intermolecular forces locking it all together, right? Okay, so some phase changes break these forces that glue the molecules together, and some phase changes create these intermolecular forces that glue the molecules together. There are really 2.5 different types of glue. There's 2.5 different types of intermolecular forces that can hold molecules together. Okay, here's a picture of water. Now, you may even know water's intermolecular force. Biology teachers love to teach water's intermolecular force, right? I work with a bunch of biology teachers, right? Okay, I'm the only chem teacher on my side of the building because I don't get along with anyone else. I'm surrounded by biologists. It's terrible. And they love to teach hydrogen bonding. None of them knows what it is. They have no clue. Couldn't describe it to you. No clue what it is. But they love to teach it. So in biology, so I mean, they probably teach it in your biology courses. Okay, they don't know what it is, but they love to teach it. That's actually the very special type of intermolecular force that water has. Before we even talk about that, so you probably heard of hydrogen bonding before. Tonight, you will learn what it actually is. The dotted lines here, these are representing intermolecular forces, a glue that is holding the water molecules together. Notice that in the solid phase for water, ice, right, you have a whole lot of dotted lines. We got a whole lot of intermolecular forces that are holding these water molecules together. Now, if you've had this before, I love this drawing. Take a look at what they have here. They have the electronegative oxygen end of one with the electropositive hydrogen end of another. So it's always red to white interacting, right? They were very careful about red to white interacting here. Look at the liquid phase for water, just regular old water. You can see that there's some intermolecular forces here. There's got to be something gluing it together, but because liquids don't have a definite shape, there's less intermolecular forces. Um, and notice also they got these sunbursts on here. This is to show that it's a dynamic process, right? So, some of the glue is being broken at one spot, but then we're getting new glue somewhere else, right? So that the amount of intermolecular forces, like in this cup of water at any given moment, the amount of forces is the same, but it's dynamic in that some are breaking and being made at any given time. It's just the number of intermolecular forces that are being broken is equal to the number of intermolecular forces that are being created. So there's no net loss of intermolecular forces. Notice that in the gas phase, they don't show any dotted lines. And that's because in the gas phase, there are no intermolecular forces. If two particles in the gas phase were to collide, they just bounce off each other. It's like an elastic collision and they go about their way. There's no interaction. They don't stop to talk, right? They just boom and they go about their way, right? And that's part of kinetic molecular theory. No interactions in the gas phase. All right. So what are the types of glue, right? What kinds of glue can we have? What types of intermolecular forces can we have that hold these molecules together in the solid and liquid phases? The answer is we can have dipole-dipole forces, we can have London dispersion forces, and then there's a very special type of dipole-dipole force called a hydrogen bond, which is probably the only one that you've ever heard of unless you had this in Chem 101 or 111. And we're going to talk about that one last. Okay, we're going to talk about that one. Well, I don't know. Maybe not last. We'll see. Um, Maybe we'll do London dispersion forces last because that was the most complicated. Let's talk about dipole-dipole. Dipole-dipole forces is the name of the glue or intermolecular force that holds polar molecules together in the solid and liquid phases. So keyword polar dipole-dipole. Polar dipole-dipole. Where does this come from? Well, this comes from the fact that polar molecules have a dipole moment because of this difference in electronegativity. Let's take a look, for example. Say we had a molecule of carbon monoxide. So I'm going to draw the Lewis structure of carbon monoxide up here. Carbon monoxide has got a triple bond between the carbon and oxygen. I'll tell you the electronegativity values, although you should be able to look at a periodic table and tell me who's more electronegative. If you look at a periodic table, oxygen's next to fluorine. Oxygen is going to have the higher electronegativity, and it does. It's 3.5. And carbon is further away, so it's going to have a lower electronegativity, and it does 2.5. So that's a difference of 1, right? So this is a polar bond. Oxygen is going to hog these 6 electrons. It's supposed to be sharing those 6 electrons 50-50. It doesn't. It hogs them. What happens? Well, when you're a polar molecule or you have a polar bond, that means that that region with the higher electronegative atom, that region is hogging the electrons, right? So like the electrons are spending all their time over here, and they only go and visit carbon every once in a while. Because electrons are negative, that's going to cause the oxygen side of this molecule to develop a partial negative charge. So this is the lowercase Greek letter delta, and in science, or in chemistry, I should say, it means partial. So this is not a -1 charge. It's not an anion, but it's a partial negative charge. They're still sharing the electrons. Oxygen didn't steal them. If it stole them, it would be a negative charge. It's just hogging them. So that's a partial negative charge. Carbon, because it's being deprived of the electron density that it desires, the carbon is going to have a partial positive charge. So it's got a delta plus on that carbon atom. And in fact, you can draw a dipole moment arrow to represent this. A dipole moment arrow describes the polarity of a bond or a molecule by taking an arrow and pointing it towards the electronegative side of the molecule and making the tail look like a plus sign. So the head of the arrow is by the negative charge, and the tail, which we made look like a positive sign, is by the partial positive charge. Give me a really, do the old raise the hand function in there. If everything I just said you got in Chem 101, how many people got polarity, electronegativity, dipole moment, all that stuff in Chem 101? Hoping, all right, there's some hands. It's certainly, all right, there we go. There we go. Okay, good. So hopefully, and again, some people haven't taken Chem 101 for like 2 years. So that should have been some review. Oh, that's good. So that looks like everybody then. So that's fantastic. Okay, that's fantastic. Okay, so hopefully y'all can see that carbon monoxide. Yeah, Bree, you better say thumbs up because I just taught this a week ago, right? Same with Sophia. Carbon monoxide, okay, polar molecule. So what kind of intermolecular force is it going to have? Well, it's going to have a dipole-dipole force. The strongest intermolecular force available to a polar molecule is a dipole-dipole force, unless it can do this special thing called hydrogen bonding, which is super rare. We're going to talk about that in a minute. So here's what happens, right? If I have two carbon monoxide molecules in the liquid or solid phase, because remember gas phase, but if I have two carbon monoxide molecules in the liquid or solid phase, here's how they're going to try to glue themselves together. We draw a carbon monoxide here and we put the delta plus and the delta minus on it because, again, oxygen more electronegative hogs those electrons. We're going to do this here, and we're going to draw another carbon monoxide, a neighboring carbon monoxide molecule over here. Oxygen, again, hogs the electrons. So delta minus on that, delta plus on that. Here's how two polar molecules are going to want to aggregate together in the condensed states of matter. Two polar molecules are going to want to aggregate together in the condensed states of matter such that the partially negative end of one is by the partially positive end of another. They're going to be attracted to it. Well, that guy's deader than dead right there. I actually made that. You can't see that, but you have to trust me. Anyway, they're going to interact like this. Okay, the oxygen, which is electronegative, and the carbon, which is electropositive, they're going to be attracted to each other coulombically. Opposite charges attract. And this is what a dipole-dipole force is. Dipole-dipole. A dipole-dipole force is when two polar molecules interact in the liquid or solid phase such that the partially positive end of one and the partially negative end of another interact and glue themselves together. Okay? That's a lot. Let's wait till I describe London dispersion forces. That's like 10 times the amount of words I got to use there. So get another example. We'll do another linear molecule. If I had, for example, I don't know. Let's say I had HCl, hydrochloric acid. Hydrogen 2.1, chlorine 3.0, difference of 0.9. Fluorine hogs the electrons, hydrogen's deprived. Two molecules of HCl are going to want to aggregate together such that the partially negative chlorine of one is interacting with the partially positive, and it doesn't always have to be in a straight line, right? I think in solution in the liquid or solid phase, it's 3 dimensions, okay? So whatever, you don't have to draw a straight line as long as the partially negative end of one and the partially positive end of another are interacting. Doesn't have to be a straight line. That's a dipole-dipole force, folks. Dipole-dipole force. Let's do hydrogen bonding now. Why not? Let's get it out of the way. Hydrogen bond is an incredibly special and strong type of dipole-dipole force. And it only exists between hydrogen, which you could probably figure out from the name, hydrogen bonding, and 3 other atoms. And that they are nitrogen, oxygen, or fluorine, NOF, or fluorine, oxygen, nitrogen, FON. However you want to think about it. A hydrogen bond is a very special and super strong intermolecular force. It's actually, I consider it to be a special type of dipole-dipole force. Very special and super strong intermolecular force that occurs between hydrogen, the hydrogen 1 molecule, and the nitrogen, oxygen, or fluorine of a neighboring molecule. Okay, we're gonna need to be a little more specific here in a moment, but at first, we'll start here with this. So the one that people know is that water can hydrogen bond, and that is very important and very special. Ask any biology teacher, they'll tell you. Water's a polar molecule. Oxygen hogs the electrons, delta minus. The hydrogens are being deprived, delta plus. And you can draw a dipole moment like that, right up through the gut of that molecule, right? And it satisfies everything we need. The arrow points towards the negative end, and the tail is by the electropositive end of the hydrogens here. Okay. What a hydrogen bond is going to be is when one water molecule, okay, interacts with another water molecule such that the delta minus of one is next to the delta plus of another. And what we have is we have an interaction between hydrogen and a nitrogen, oxygen, or fluorine on a neighbor. When you have a hydrogen interacting with a nitrogen, oxygen, or fluorine of a neighboring molecule, you have the potential to have a hydrogen bond. There's going to be one other caveat we're going to put in here in a moment, but you're not ready for it. Okay, but just notice how this satisfies the definition that we just talked about. We have a hydrogen interacting with a neighboring nitrogen, oxygen, or fluorine. That's a hydrogen bond. Okay. Water is not the only molecule that can hydrogen bond. Hydrofluoric acid could hydrogen bond. Delta negative on the fluorine, delta positive on the hydrogen. We have a hydrogen bond right here because we have a hydrogen interacting with nitrogen, oxygen, fluorine of a neighboring molecule, hydrogen bond. What makes hydrogen bonds so darn special? Well, they're super special and super strong for two reasons. Okay, number one, number one, nitrogen, oxygen, and fluorine have large electronegativities. Nitrogen's 3.0, oxygen's 3.5, and fluorine is 4.0. This is like valedictorian, salutatorian, and the other guy, right? Nobody cares about third place, right? I was the other guy. No, I wasn't even third in my graduating class. Anyway. Valedictorians. Tell you, make such a big deal out of it. My valedictorian, he got a full ride to Carnegie Mellon when I graduated, and I don't know what happened, but he dropped out after a year, and I managed to target. It's like, I saw him the other year. Doesn't valedictorian the following year, she dropped out, and she works at Long and Ecker's True Value Manhunt. It's like doesn't. I don't think it's a good indicator always of what's going to happen, which is why I think the class rank thing at Township, I think I rid of it. It's stupid. It's like it doesn't matter anyway. Doesn't matter. Anyway. Fluorine, nitrogen, and oxygen, top of the class. High electronegativities. What that means is that these are very polar bonds. When you have fluorine and nitrogen and oxygen around, there's a lot of hogging of the electrons. Those three atoms really hog electrons. So this is an incredibly polar bond. So this partial positive charge on the hydrogen is pretty high, right? And that partial negative charge on the nitrogen, oxygen, fluorine, pretty high. So you have large partial charges, it's like an oxymoron. And when you have large partial charges, you get a strong interaction. So that's the primary reason. The other reason we're not going to get into, and I could talk to you for 4.5 hours probably about this, because my master's thesis was on nitrogen, hydrogen, fluorine, hydrogen bonding. I made the shortest nitrogen, hydrogen, fluorine, hydrogen bonds ever been made, right? Okay, not a big deal. Who cares, right? I don't even care. Okay, but that was my ticket out of grad school. Anyway, the small size of nitrogen, oxygen, or fluorine is also really important because since they're so small, they can get really close together. And the closer the two molecules together can get together, the stronger that interaction is going to be. So it's the high electronegativities and the small size of nitrogen, oxygen, fluorine that makes this interaction between a hydrogen, nitrogen, oxygen, fluorine really, really, really strong. How strong? It depends. Usually it's about 4 times stronger than your typical dipole-dipole. So hydrogen bonds at least 4 times stronger, somewhere around 4 times stronger than your typical dipole-dipole. It's an anomaly, so we make an exception. We have a special name for it. We call it hydrogen bonding. Okay. Without hydrogen bonding, if water just did a dipole-dipole, right, there'd probably be no water on this planet, right? Because water is a tiny little molecule. It would not be a liquid or solid on Earth, really, okay, except for maybe at the poles, okay? But thankfully for hydrogen bonding, we got a lot of water. We got a lot of water. We got a lot of life on this planet, which is great. At least I think it's great. Maybe a little too much life, right? How many people are we up to now? 9 billion, something like that? Nuts. No end in sight? Okay. Hydrogen bonding, one more caveat. Here we go. Hydrogen bonding, one more thing to worry about. The hydrogen has to also be intramolecularly. I didn't make it. There we go. Has to be intramolecularly bound to a nitrogen, oxygen, or fluorine. To be more specific, it's got to look like this. The hydrogen has to be intramolecularly bound to nitrogen, oxygen, or fluorine, and it has to be intermolecularly interacting with a nitrogen, oxygen, or fluorine. Draw this, and then we'll talk. That is so good. I'm a Starbucks guy. Dunkin' Donuts, terrible. My wife ran out. There's the Dunkin' Donuts close to where they were going to the library, and I said, "No, please no. Drive the extra 2 minutes. Give me some real coffee." All right, here we go. Let me give you an example of something that people think is hydrogen bonding, but is not. Formaldehyde. There's our Lewis structure for formaldehyde. Formaldehyde is a polar molecule. Oxygen, high electronegativity, it's going to hog those electrons. Delta minus here, delta plus on this end. So we got a dipole moment arrow going right up through the gut. That is a polar molecule, folks. How are two formaldehyde molecules going to want to interact? Well, two formaldehyde molecules are going to want to interact where the partially negative end of one, by the way, that's a trigonal planar molecular geometry with bond angles of 120 degrees. Trigonal planar can be nonpolar, but see, all three of these X groups are not the same. So this is a polar trigonal planar. Trigonal planar can be nonpolar, but only if they're all the same. That one's different. This is a polar trigonal planar. Vesper, if you're taking organic chem, go back. That sheet that I showed at the beginning of class, get that in your brain. You don't really need it for 102. Get it in your brain for organic chemistry. If we look at this, one formaldehyde molecule is going to want to point its partially negative end at the partially positive end of another. And you get a scenario where an oxygen of one is interacting with a hydrogen of another. And you would be quick to say this is a hydrogen bond, but you'd be wrong. Because the hydrogen bond has to be intramolecularly bound to a nitrogen, oxygen, fluorine as well. Because if the hydrogen is not intramolecularly bound to a nitrogen, oxygen, fluorine, this is not a polar enough bond. That's not a great enough delta plus. You see, the carbon is bound to the oxygen, but that hydrogen is not. So this is not a hydrogen bond. This is just a dipole-dipole. It's just a dipole-dipole. Now, if we go back and look at water, see, this checks the boxes. We got a hydrogen intermolecularly interacting with a nitrogen, oxygen, fluorine, and it's intramolecularly bound to a nitrogen, oxygen, fluorine. We got an oxygen on that end and an oxygen on that end. Right. Watch out for that. Okay. So a lot of times when people get hydrogen bonding, they don't get this level of explanation with it, right? Because they're teachers. I mean, I bet professors that would tell you that's a hydrogen bond. They just have no idea what they're talking about. It's tough. There's a lot in chemistry. It's a lot going on. So many little details and stuff. And if you hadn't, you didn't focus on hydrogen bonding, like until I studied in graduate school, I might have even said that was a hydrogen bond, right? It's just there's a lot going on in chemistry, right? Okay, cool. Love that. Love that. We talked about dipole-dipole. We talked about the special kind of dipole-dipole called a hydrogen bond. Let's do the last intermolecular force called a London dispersion force, which is what nonpolar molecules use. And then we'll take our break. But it is going to take me a solid at least 10 minutes to describe London dispersion forces to you. Ah, the force with so many names. London dispersion forces, we often abbreviate to LDFs, and these used to be called AKA, also known as Van der Waals interactions. So if you see Van der Waals forces, same thing as an LDF, same thing as a London dispersion force. All right. This is how nonpolar molecules hold themselves together in the condensed states, meaning solid and liquid phases. Oh boy. What is a London dispersion force? At first, this is going to make no sense, and we're going to describe it, but let's write it down. A London dispersion force is an instantaneous dipole moment that randomly forms in a nonpolar molecule that induces the opposite distortion in a neighboring molecule and therefore creates a brief moment of attraction. Woo! Take a second, write that down. and we will take a solid 10 minutes or so to explain. What's up, Angel?
So when I first learned about London dispersion, we were told that all bonds, I guess, have London dispersion forces. Is that true?
All covalent compounds have some amount of intermolecular forces. We're going to get to that. I cover that after I covered all the forces. That's right. So to be more specific, and I do go back and clean this up, I promise. After the break, we're going to clean this up. Nonpolar molecules, LDF is the only force available to them. Okay. Polar molecules do have LDFs, and polar molecules that can hydrogen bond also have LDFs. They're just not usually significant unless they're a large molecule. I promise we're going to clean that up. I don't mention that because people are already like, right? So I don't just hold off. But absolutely, you are absolutely right, Angel. Give me like 30 minutes, right? And you don't clean that up. Yep. But take a look at this statement a little closer. Okay, it's the only significant force in a non-polar molecule. So that's why I kind of chose my words here carefully. Yep. Yep. All right. Take another second, write that down. And then, yeah, we're going to do this thing. All right. Let's do it. Yeah, it's one of those topics. It's just so much. It can be so confusing. It's like, there's a lot of little details. It's like, when do you cover hydrogen bonding? When do you cover what forces are in each type of molecule? It's like, I like to go through each individual force, and then we double back. Yeah. All right. Here we go. Let's look at F2. F2, that's a non-polar molecule there, ladies and gentlemen. Fluorine, even though it's a valedictorian, it's got an electronegativity of 4.0. We got two fluorines bound together. They're fighting over those electrons that they're sharing, those two electrons in that single bond, but ain't nobody winning. Okay, so this is a non-polar molecule. Fluorine at room temperature is a gas, but if we cool it down, we can turn it into a liquid. And if you keep cooling it, you can turn it into a solid. Okay, so when it's in its liquid phase, when it's in a solid phase, how are the fluorines interacting? What force is holding them together? Well, this gets complicated, man. So I'm going to draw a neighboring fluorine molecule here. I urge you to do the same. Give a little space between the two. So I'm going to draw how two fluorine molecules, which are each nonpolar, would interact with each other in the liquid or solid phases. How could they possibly do this? Well, the only way they have, because they're nonpolar, the only way they have to interact is to use a London dispersion force or van der Waals interaction. Here's how it works. I want to talk about the electron clouds of these molecules. So if you find fluorine on the periodic table, fluorine has an atomic number of 9. Okay, that means each fluorine has 9 total electrons. I'm not talking about valence electrons, it's got 7 valence, but I'm talking about the entire electron cloud, right? So fluorine has a total of 9 electrons. So if I have a molecule of F2, each fluorine is bringing 9 electrons with it. So each molecule of F2 has got 18 electrons whirling around, making up its electron cloud. Again, 9 and 9, that'd be 18 total electrons. Now, for a nonpolar molecule at any given moment in time, it's safe to assume that that electron cloud is symmetrical. Okay, so what does that mean? Well, that means if I draw this, let's imagine we have the electron cloud and we cut it in half. We got a top and a bottom half. And at any given moment, they should be symmetrical. So that means there should be 9 electrons on the top and 9 electrons on the bottom. Okay, I'm going to do the same thing with this fluorine molecule. We should have 9 electrons on the top and we should have 9 electrons on the bottom of these molecules' electron clouds. Here's what a London dispersion force is. Buckle up, folks. A London dispersion force is when the electron cloud randomly gets distorted. Here's how that's possible. At any given moment, there should be 9 electrons on top and 9 electrons on the bottom. But these electrons are not stuck on the top and bottom. There are electrons going back and forth, right? It's just that at any given moment, if one electron goes up, one should come down at the exact same moment in time, and we should still have 9 and 9. But you can imagine that if these electrons are whirling around the molecule, right? Okay, that maybe an electron goes up, whoop, and one doesn't come back down right away. And for a moment in time, I have 10 electrons on the top and 8 electrons on the bottom. Hopefully, you can imagine this scenario. And for this brief moment in time, and we are talking like a femtosecond here, people, like a billionth of a second. That's the time scale that we're working on here. It's crazy to think about, folks. Okay, but for like a billionth of a second, this molecule's electron cloud is not symmetrical, right? For this billionth of a second, I have a bigger electron cloud on the top, and I have a smaller electron cloud on the bottom. And what is that going to do? Well, at the top of this molecule has more electrons. We're going to have a very slight delta minus on the top. And if the bottom side of this molecule has less electrons, we're going to have a very slight delta plus on the bottom. What is that going to do? Well, what that does, it's crazy, is if I got a neighboring fluorine molecule hanging out that's balanced, right, and symmetrical, if I have a neighboring fluorine molecule that's hanging out, and now it's exposed to a partial positive charge, the electrons in this molecule are going to be attracted to that. And what they're going to do is all the electrons in this molecule are going to shift towards that partial positive charge. So all the electrons in this molecule are going to go, boop, they all kind of just rush up. And the electrons just got moved. They all sort of migrate towards that. And now this molecule's electron cloud is going to become distorted because the electrons were attracted to the partial positive charge in this molecule. This molecule's electron cloud shrinks down here and grows up here. We get a delta minus here and a delta plus here. What happened? This molecule had a random instantaneous distortion of its electron cloud that induced a distortion in the neighboring molecule's electron cloud. And what we now have for a billionth of a second is a partial positive charge next to a partial negative charge. And that, ladies and gentlemen, is a London dispersion force. That phenomena cannot be described in less than 10,000 words. It's impossible. Can't do it. Okay? It's complicated. It is absolutely complicated. Okay? When you have an otherwise symmetrical electron cloud, okay, it can become randomly distorted. We're going to talk about how you can influence the odds of that random distortion in a moment. That's called polarizability. Okay, but the electron cloud can become randomly distorted, inducing a distortion in a neighboring electron cloud. And for a billionth of a second, you get a partially negative and a partially positive next to each other in space. They have a small attraction to one another. That is the London dispersion force or Van der Waals interaction. Now, how can you increase the likelihood of this happening? The answer, bigger electron clouds. For fluorine, not a lot of electrons, 18 total electrons. The odds of an electron being in the wrong place at the wrong time, not very good. That's why fluorine's a gas at room temp. At room temp, okay, the electrons move so fast that they don't end up on the wrong side long enough, and it's not enough to hold fluorine together in the liquid or solid phases. But bromine is a liquid at room temperature. It's a nasty orange liquid. If you take organic chemistry, you might get to work with it, although in a lot of organic labs trying to be a little more environmentally friendly, they stop working with the bromine. They actually make it in situ now. But bromine, if you find bromine on the periodic table, bromine got 35 electrons. So we got a bigger electron cloud now. You got 35 electrons and 35 electrons. And what happens here is now, as the size of your electron cloud increases, the likelihood of a distortion occurring also increases. It's like buying lottery tickets, right? You do not have a good chance of winning, but the more tickets you buy, the greater the chances you have of winning, right? It's that simple. The more electrons you have, the greater the chance you have of one of them being in the wrong place at the wrong time, creating a distortion, okay? So bromine, now its electron cloud is big enough that you have enough distortions that bromine is a liquid at room temperature. So there's enough intermolecular forces, enough random distortions, enough London dispersion forces going on that two bromine molecules can stick together in the liquid phase. And iodine is actually a solid at room temperature. And the reason that iodine, I2, is a solid at room temperature is because each iodine is bringing 53 electrons with it. Whoops. Huge electron cloud, 53 and 53. And now we have so many electrons that the random distortions happen enough that this holds it that at room temperature, it can congeal as a solid. There's enough London dispersion forces holding it together as a solid. This phenomenon is called polarizability. Polarizability. What that means is the larger the electron cloud, the greater the chances of a random distortion occurring. I love it. What time is it? 7:27. I tell you what, we're gonna get to the fact that everybody's got LDF here before the break. It's fantastic. I got 3 minutes. We'll take our break at 7:30. All right. That gives me just enough time to talk about this, folks. Angel's absolutely right. London dispersion forces occur in all molecules, even polar ones. Think about it. If you're a polar molecule, like, I don't know, how about HF? No, I don't like that one. How about carbon monoxide, we did earlier? This molecule's electron cloud is already distorted. Oxygen is hogging the electrons. So if we think of the electron cloud of this molecule, do it in purple. Electron cloud of this molecule might look something like that, where the electron density is all over here, right? But this is how the molecule naturally is, right? Because oxygen is hogging the electrons. But the electrons are still whirling around, right? There is still the odd. This is the molecule's natural state. But there's still the odds that the electrons could just even spend even more time over here, and the molecule could become even more unsymmetrical at any given moment in time. Right? You can still have a random distortion in an already distorted molecule, electron cloud. You know what I'm saying? Like, it's crazy. It's like this molecule's electron cloud was already distorted, just randomly, because the electrons are moving around. It could randomly become even more distorted. Now, carbon monoxide is polar. So the strongest intermolecular force available to it is dipole-dipole. But it can and does have a little bit of London dispersion force happening as well. Now, this generally does not matter unless you have a ridiculously large molecule. If you have a ridiculously large molecule, the bigger the molecule, the more that the LDF is going to take over. So if you have a polar molecule and it has a really large molecular weight, there is a chance, since it's so big, it's a big polar molecule. Let's say it's big. If it's a big polar molecule, there's a chance that the LDFs could actually have more of an effect than the dipole-dipoles. But that is some heavy crap, man. That is some super heavy crap, right? That I say is beyond, a little beyond 102. Okay. You got to be careful of how a question is worded. Does the question say what is the strongest intermolecular force available to this molecule? Because then you're saying, well, does it have hydrogen bonding? No. Okay, well, then does it have dipole-dipole? No. Okay, then it's LDF, right? Or is it saying what are all of the intermolecular forces available? If it's asking what are all of the intermolecular forces available, then if you got hydrogen bonding, you also have dipole-dipole. And if you got dipole-dipole, you also have LDF. And if you have dipole-dipole, you got LDF. But if you're non-polar and all you got is LDF, all you got is LDF. So everybody's got LDF, right? You kind of work down from there. Hydrogen bonding also has dipole-dipole and LDF. Dipole-dipole also has LDF. LDF is just LDF. So that's kind of like what's the question asking? What's the strongest force, or what are all of the forces? So you got to be careful what it's asking for. Okay. And in the homework, sometimes I say, what's the strongest force? Sometimes I say, give me all the forces available. Then you got to list them all. It's a polar molecule. Okay, I would like you to take a look at these molecules: N2, NH3, C4H10, and we already did CO, so hopefully you can get that one right. I would like you to tell me what is the strongest intermolecular force that would hold these molecules together in the condensed state. So take a minute, give me the strongest intermolecular force, and then we're going to go over it. So do it. N2, we got ourselves a non-polar molecule, folks, right? That's going to be just LDF, London dispersion forces. NH3, we got ourselves a polar molecule, but it ain't just polar. That's actually a trigonal pyramid molecular geometry with that beautiful stuff. If you're going on to organic chemistry, you got no idea what I'm talking about there. That's bad news bears. Vesper, VSEPR, memorize it. Anyway, we got NH3 here. Okay, that's a polar molecule. We have a hydrogen. Why is it polar? Nitrogen more electronegative than hydrogen. We got a dipole moment going right up through the base of the trigonal pyramid molecular geometry. The hydrogen delta plus, nitrogen delta minus. What's that going to do? Well, we can have a neighboring ammonia molecule over here that it is going to interact with. We have a nitrogen intermolecularly interacting with a hydrogen that's intramolecularly bound to a nitrogen. So that's going to be a hydrogen bond. Hydrogen bond. Okay, what else does it have? It's also got dipole-dipole, and it's also got LDF. But the strongest force by far, hydrogen bond. This one, you don't even have to draw the Lewis structures for, folks. That is a molecule that contains nothing but carbons and hydrogens. That is a hydrocarbon. Hydrocarbon. And when you see an organic molecule that contains nothing but carbon and hydrogen, immediately nonpolar. And if it's nonpolar, all it's got is LDF. You don't even need to draw the Lewis structure. That's butane, by the way, stuff found in lighters. CO, we did that one earlier, right? A bunch. CO, polar molecule, delta minus on the oxygen, delta plus on the carbon. Since it's polar, it's got dipole, dip, and it can also LDF, but dip is the strongest dipole. That's the strongest intermolecular force available. How'd we do on that? Hopefully all right. All right.